Hello, I am Alejandro Lumbreras-Calle, and I'm going to give you a talk about extreme emission line galaxies in the local universe, a new sample unveiled with the J+ survey. Thank you for listening to this video. And I am a postdoc at the CEFCA Institute in Spain under the supervision of Carlos López San Juan and with the collaboration of some colleagues in the IAA. So I guess this is a bit redundant in this conference, but the star formation is really important in the evolution of galaxies, and studying how these star-forming galaxies evolve and change along the history of the universe is crucial to understand the changing physical processes of the star formation and the evolution of the universe itself. Since the 1960s, different surveys have discovered in the low redshift or nearby universe samples of compact, strongly star-forming galaxies. They have been given many different names. I will use extreme emission line galaxies, and they have been discovered using many different observational approaches, objective prism, spectra, narrowband, multiband surveys. And of course, these objects are interesting by themselves. How do they evolve and appear? But is there any other reason to study them? Well, of course, since we are all in this conference, we are interested in the similarities between the very high redshift reionization era galaxies and these local starbursts. Some of the shared characteristics are low masses, high specific star forming rate, low metallicity, high ionization, and sometimes Lyman leakage. So these first galaxies in the universe hold many different interesting. I will point out a couple of interesting things, the population 3 stars that may have, and the way and if they are responsible for the reionization of the universe. And analyzing perhaps in much detail, since we can, the very low redshift galaxies that look like them may help us understand the very high redshift ones. But in order to analyze them, first we have to find them. And we can find them using the J+ survey. This survey is a very wide and multiband photometric survey done from this 80-centimeter telescope at the Javalambre Observatory in Teruel, a relatively new observatory, which is in 6 broadband and 6 narrow medium band filters that you can see here, reaching magnitude 21. Is scanning the universe as a precursor of another survey, J-PASS, with 56 narrowband filters from the big 2.5-meter telescope. You can access the data here. It's really easy. And there's also a southern telescope doing a very similar survey. So how did we select the extreme emission line galaxies? Well, we focused only in the J0515 filter, which is at this wavelength with 200 angstroms wide, covers the oxygen 3 doublet emission at the very low redshift universe. So we focused on objects that had a lot of flux in this filter compared to the R filter, which is here, which, taking into account, well, the H-alpha emission and the slope of the continuum, mostly the R traces the continuum underneath, but we will do it better later. We got 30,000 objects this way, but when we check the available spectra for these objects, which were 2,500 spectra, well, we see that in fact the majority of them are not low redshift galaxies. They are high redshift quasars with different emission lines that fall in that filter. So how did we get rid of those? Well, we tested a few things, and the most efficient one was looking at the WISE data in the infrared. Using the UNWISE catalog, we built these color or color magnitude diagrams using optical infrared colors, and we saw that the low redshift galaxies and quasars separated very clearly. Those that were spectroscopically confirmed separated very clearly in these diagrams. So we could trace these blue squares to select a very pure and very complete sample of candidates, which ended up being 1,005 500 galaxies. We then analyze in detail these candidates, performing SED fitting using the Seagull software, and well, two startup populations with relatively instant burst of population, a very young one, and a relatively wide range in mass ratios, metallicity, status extinction, etc. You can see here one example of this fit with the old population, the young one here, and the stellar continuum and the nebular emission on top of it. You can see here that it's really, really important to model the nebular emission for these galaxies. So this gave us some data, the continuum flux, for example, in order to measure the equivalent width more accurately. And we found 466 galaxies with equivalent width above 300. This is the limit we set for the extreme emission line galaxy sample. It's very important that out of these 466, 410 were not previously classified as extreme emission line galaxies in any way. This sample had a very young burst of star formation in general, over the 6 mega years, low stellar masses that you see here. The old population nevertheless dominated the stellar mass. The extinction was low as well, and the relatively low metallicity as well. When we compare this, our results using the J+ photometry with the SDSS spectra, we see that they match very, very well. This is really important for us in order to give the results and the derived results with confidence. You can see here the equivalent width measure in the 515 filter traces the one-to-one relationship very nicely with the equivalent width measure in the Sloan spectra. The same can be said about the fluxes in oxygen 3. This time estimated using Seagull on the J+ data, and this is the spectroscopic result. Even for the R-band equivalent width, which is traces basically equivalent H alpha, and also the photometric redshift, it's really, really good. The sigma MAD is really low, order of 0.03. So this gives us confidence in the rest of the analysis. When we compare this result with previous work, we can look to broadband selection surveys like those for the blueberry galaxies and the green pea galaxies, and also for spectroscopic surveys. The broadband surveys have some advantages over us. They have wider areas and deeper observations, and in some cases broader redshift ranges, but they have some disadvantages. They are less efficient in finding extreme emission line galaxies. They need to find even more extreme systems. You can see here the line is the selection function for the blueberry galaxies, which are in black triangles here, and we can push much inside the typical colors for SDSS galaxies that are in these dotted contours, while still being very certain that we are finding extreme emission line galaxies. Since we are using a medium band filter, we don't have to restrict ourselves to very extreme broadband colors. This also helps us to find targets that look similar to extremely metal poor galaxies, with perhaps related with the fact that we are not biased towards high oxygen 3 to H alpha ratio. Spectroscopic surveys, of course, have deliver much more physical information with much more precise line and redshift measurements, but they as well are much more time consuming, and they have to select some galaxies to observe, which is a certain bias in general towards brighter sources. This is another comparison with previous work. We computed the number density of ELGs for our sample, which gives like roughly 1 per 4,000 megaparsec cube megaparsecs. But how does this compare with other previous works? Well, you can see here that we took extreme care in making fair comparisons, limiting in equivalent width and magnitude or mass, and redshift range as well. And first, you can see that we find 10 to 50 times more extreme emission line galaxies than what broadband service could do, like Blueberries or Greenpeace. In contrast, we find roughly similar amount of galaxies when we compare with magnitude limited spectroscopic surveys. This seems to imply that we are just as good as them in finding this kind of galaxies, only we go deeper. And well, it's comparable with these results from narrowband surveys, but they have wider error bars in this case. So we analyze the morphology of the sample as well. The majority are compact, as you see here. Some do show some extended emission around the compact region, and others show really complex morphology, extended, etc. The extended objects, in fact, have slightly higher masses and slightly lower equivalent widths in oxygen-3. We rejected star-forming regions in larger scale spirals. So, analyzing a bit more in depth the sample, we can estimate the star-forming rate. We do that using the H-alpha flux and correcting with the extinction value that we have, which is online with what the available spectra tells us. And we see that our sample of galaxies in red lies way above the local main sequence relation. In fact, it's more similar to values reached or expected to be reached by typical galaxies at redshift from 1 to 5. And the same can be said about the oxygen-3 equivalent width. When we compare it as a function of mass, we have also values more comparable to very high redshift, well, at least 2, 3, than slightly lower one. After all this analysis, we wanted more. We need more data to analyze these galaxies with more precision. So we went and took a spectra with the INT telescope in La Palma, which will hopefully the volcano stops soon and they can resume their lives. So we observed 33 galaxies, only 2 with IFU from Calar Alto. We'll focus on the long slit spectra, which of course is still preliminary, but all 33 of these galaxies are in fact extreme emission line galaxies, and we can see their strong emission lines. And preliminary data reduction on the first 6 targets shows, well, a good correlation with the Sigal estimated values that we have, as we have shown with the Sloan spectra. Some of them detection with the auroral oxygen-3 line, and we could perform some metallicity estimation nevertheless. And we saw that, well, they have low metallicity, below 8, but it's relatively expected given their low masses. But in some cases, we do go below these. So maybe we are populating an interesting region of low metallicity galaxies with slightly higher masses than what is used. But what we can see is that the oxygen-3 to oxygen-2 ratios are really, really high, at least in these 6 galaxies. They are almost record-breaking, alongside, of course, these isotope papers. So this indicates high ionization parameter, perhaps density-bounded H2 regions, and who knows, maybe Lyman leakage. This is not so simple, but it's an interesting idea. So, as a summary of this work, well, I can remind you that using this medium band filter over 2000 square degrees, we compile a very large sample of extreme emission line galaxies at low redshift, 400 of them previously unknown. So it's very efficient, relatively unbiased selection with high purity and high completeness. SED fitting of this sample reveals young, low mass galaxies with little dust extinction, with a very high specific star formation rates and equivalent width comparable to high redshift. And the follow-up spectroscopy that we have performed tells us that we are indeed finding extreme emission line galaxies with probably low metallicities and certainly extreme oxygen-3 to oxygen-2 ratios. and maybe this leads to the identification of new extremely metal poor galaxies and candidates to have Lyman continuum leakage. So in future work, we will analyze in more depth these spectra, and we will move on and find higher redshift extreme emission line galaxies. And with JPAS, we will analyze in much more detail and fainter targets. And all this work, except for the spectra, will be appearing in the archive very soon, probably this week, if not the next one. And well, I am available for any questions or comments that you want to make in the Slack, by email, or on Twitter, whatever you prefer. Thank you for listening.